This video aims to teach you how to make use of an IC table. This IC table is very applicable to the topic in chemical equilibrium. We usually use the IC table to do calculations found in chemical equilibrium. Before we talk about the IC table, first and foremost, it's good to talk about equilibrium constants. Generally, you will find yourself required to use equilibrium constant and use them in conjunction with the IC table. We'll start off with a hypothetical equation that uses A moles of A reacting with B moles of B to give us C moles of C and D moles of D. Now, for an equilibrium constant, what happened here is that to get our equilibrium constant is basically the concentration of C power C multiplied by the concentration of D power D divided by the concentration of A power A multiplied by concentration of B power B. Now, essentially, the Kc is just basically the concentration of the products at equilibrium divided by the concentration of reactants at the equilibrium. So what happened here is that in equilibrium constant, you are making use of the concept of dynamic equilibrium. Do note that the Kc expression excludes substances which are in the solid or liquid states. Generally, you also should take note that the concentration of water is excluded in aqueous equilibrium. Do note something very useful about the Kc expression. The unit for the Kc will be mole per dm cube power C plus D minus A plus B. The other equilibrium constant that we normally talk about will be for Kp, and Kp will be to assume that A, B, C and D are all gaseous systems. If they are all gaseous, what happened here is that the Kp expression will be the partial pressure of C power C multiplied by the partial pressure of D power D divided by the partial pressure of A power A multiplied by partial pressure of B power B. Now what happened here is that, like the Kc expression, the Kp also makes use of the concept of dynamic equilibrium. It is applicable for gaseous reactants and products. Do note that for this particular scenario, for the Kp expression, I've basically assumed that A, B, C and D are all gases. It is what I've mentioned earlier. The units for this Kp expression will be atmospheric power C plus D minus A plus B, or Pascal power to C plus D minus A plus B. Now, depending on the units of the pressure used, we either use atmospheric or Pascal. The first example we'll be using the IC table will be to basically help us with the calculation in chemical equilibrium. The question is as follows. In a vessel, the initial concentration of hydrogen gas, iodine gas, and hydrogen iodide are 0.75, 0.83, and 0.11 mole per dm cube respectively. The concentration of hydrogen gas is 0.15 mole per dm cube. When the equilibrium is established at 731 Kelvin, calculate the Kc for the reaction of hydrogen plus iodine to give us hydrogen iodide. This reaction is an equilibrium. Now what happened here is an IC table is usually used to help to perform the calculation. What happened here is that in the IC table will contain the initial, which is the I, which represents the initial amount, concentration or pressure. The C represents the change in the amount, concentration or pressure, whereas the E represents the equilibrium amount of or concentration or pressure. Now the E is essential in this particular question because in order for us to calculate the Kc, we will need equilibrium concentrations. This is an example of how an ICE table will look like. You could see that you can have the equilibrium reaction equation that is shown above, and you have the rows that says I, C and E. The units are also shown. So the question tells us that hydrogen, iodine and hydrogen iodide have the initial concentrations of 0.75, 0.83 and 0.11 mole per dm cube respectively. At the equilibrium, we are left with only 0.15 mole per dm cube. What happened here is that by simple mathematics, you would be able to deduce that there must be a loss of 0.6 mole per dm cube of hydrogen. Now what happened here is that the rho for change actually corresponds to the stoichiometric ratio that is found in the above equilibrium equation. Hence, using that information, we can actually find out what is the change in terms for iodine as well as the change in terms of hydrogen iodide. The mole ratio of hydrogen and iodine are in the 1:1 ratio. I've lost 0.6 moles per dm cube of hydrogen. Therefore, I will also lose the same 0.6 mole per dm cube for iodine. However, since the mole ratio of hydrogen and hydrogen iodide is in terms of 1:2, the change will be an increase of 1.20 mole per dm cube. Now to find out the equilibrium concentration for iodine is simply 0.83 subtract 0.60 to give us 0.23 mole per dm cube. And to find out the equilibrium concentrations for hydrogen iodide will be 0.11 plus 1.20 to give me 1.31 mole per dm cube. Now as you can see that in order for the equilibrium values to be substituted into the Kc expression, we need to ensure that these values are in mole per dm cube or can be converted to mole per dm cube. Now for example 2, we will talk about more calculation in chemical equilibrium. Notice that in example 1, I did not give you the Kc value. That's because it could be easily substituted. But for example 2, we are talking about sulfur dioxide and sulfur trioxide equilibrium system. What happened here is instead of like in example 1, we started off with the reactants or the substances on the left hand side. This time round, this example starts off with a substance that's only found on the right hand side. So for 1 mole of sulfur trioxide is placed in a 2 liter vessel initially. When the equilibrium is reached at a particular temperature, the vessel is found to contain 0.54 moles of sulfur dioxide. Calculate the Kc for the reaction stated above. So once again, we will use the IC table as we seen. You could see that the equilibrium of sulfur dioxide reacting with oxygen to give you sulfur trioxide is shown as above. You would have the rows I, C and E. So now let's fill in the rows from the questions that we have seen. From the question, you do know that you started off with the initial sulfur trioxide concentration of 0.50. There isn't any sulfur dioxide nor oxygen, so both of them are 0. What you do know is that at equilibrium, you have obtained 0.27 mole per dm cube of sulfur dioxide. So what this information helps you is to let you know what is the change for sulfur dioxide. The change for the sulfur dioxide, it will be a plus 0.27 mole per dm cube. Now notice that in this row, when we talk about the change, you can use the stoichiometric ratio. Since 2 moles of sulfur dioxide reacts with 2 moles of sulfur trioxide, you would expect that the change for sulfur trioxide would be minus 0.27 mole per dm cube. Whereas for 2 moles of sulfur dioxide reacts with 1 mole of oxygen, you would expect the increase in oxygen to be positive 0.13 mole per dm cube. What happened here is, therefore at equilibrium, you would have 0.135 mole per dm cube of oxygen, and at equilibrium, you would have 0.23 mole per dm cube of sulfur trioxide. The Kc expression for this equation will be simply the concentration of sulfur trioxide square divided by the product of the square of the concentration of sulfur dioxide and the concentration of oxygen, which is equals to 0.23 squared divided by 0.27 squared multiplied by 0.135. This number, as you could see, are taken from the last row. To solve, we will be able to get a value of 5.375, and using the units, or should I say the powers that we see in the units, we are able to obtain the units for the Kc expression as well. Do remember that on all calculations in this stage, we will round them up to 3 significant figures. One final note about this slide is do take note that you can actually use amount or the number of moles as units for your ICE table. But you must remember to divide it by 2dm cubed to obtain the equilibrium concentration, because your Kc expressions make use of equilibrium concentrations. Our third example is to calculate concentration from a Kc expression. This time round, you are given the Kc. The Kc for the reaction for A aqueous converting to C aqueous in equilibrium is 0.50 at 75 degrees Celsius. A solution of A, which has an initial concentration of 15.0 mole per dm cube, is allowed to reach equilibrium at 75 degrees Celsius. You are to calculate the concentration of A and C at equilibrium. So once again, we make use of our ICE table. As you could see earlier, A and C is found on the top of the row, whereas ICE will fill in the remaining rows of this table. So we have 15.0 mole per dm cube of A at start with 0 mole per dm cube of C. So let the change of A be X. So we need let the X to be the change of A. Since it's in the 1:1 mole ratio between A and C, you would expect C to gain X mole per dm cube as well. So when you do the subtraction, it will be 15 minus X. For C will be just X. The Kc expression is concentration of C divided by concentration of A, which is 0.5 divided by X divided by 15 minus X. Eventually, you will solve for X to be 5 moles per dm cube. It's now timely to do a summary of the ICE table so that you will be quite clear. We've seen 3 examples of how ICE table can be used. Of course, the list of questions that we can use for ICE table is really pretty much non-exhaustive. What happened here is, do take note that the units of ICE table can be mole per dm cube, could be moles, could be Pascal, could be atm. However, when using mole per dm cube in the units for the ICE table, you must be certain that the volume stays the same for the question, for the reaction. So in our earlier 3 cases, we generally use mole per dm cube in the ICE table was because we were quite certain that the reaction vessel's volume stayed the same. Why are we so particular about concentration? It's because concentration can be affected by volume and can be affected by amount of substance. So if your ICE table is going to use mole per dm cube and there is also volume changes, your concentration changes can be actually due to the volume change rather than the amount of substance being changed. The second row of the ICE table is quite crucial because the second row of the ICE table relies on the stoichiometric coefficient, whereas we use the third or the final row on the ICE table for our Kc expression calculation. I think it's apt to talk about Kp and the units of Kp. We have talked much at length about Kc, so let's first talk about Kp. Kp. Deduce expressions for Kp for the following reactions. State the units of Kp if partial pressure is in atm. For example A, the Kp expression will be partial pressure of nitrogen dioxide power 2 divided by the partial pressure of N2O4. The units would be atmosphere. For example B, the Kp expression will be just partial pressure of carbon dioxide. That's simply because calcium carbonate and calcium oxide are both solid. They would not contribute to any significant pressure to the system. Hence, the units of this Kp expression will be just atm. A good reminder about Kp expression, that the Kp expression is just about gases. It does not include solid or liquids. These states contribute to very little or no pressure to the overall equilibrium system. Now, in doing Kp calculations, we will need to often apply Dalton's law of partial pressure. That's because in a system which is made up of numerous gases, each constituent gas will exert its own pressure, and when they exert their own pressure, this is also known as partial pressure. The total pressure, or PT, of the system is the sum of all the constituent gas partial pressures. Hence, Dalton's laws of partial pressure, when we have a system containing A, B, and C, and all three of them are gases, the total pressure of the system will be the partial pressure of A plus partial pressure of B plus partial pressure of C. Now, how do we get these partial pressures? Partial pressure of A, for example, is equals to the mole fraction of A multiplied by the total pressure of the system. How do we get the mole fraction of A? Simply will be the amount of A divided by the total amount of gases. Our next example, example 5, which calculates Kp. This example actually applies Dalton's law. Now, once again, we are facing the sulfur dioxide reacting with oxygen to give us sulfur trioxide reaction. This is the contact process. I'm certain we are all quite familiar about it. We started off with 3 moles of sulfur dioxide, 3.60 moles of oxygen, and 4.80 moles of sulfur trioxide were heated initially in the vessel. The vessel contains 2.60 moles of sulfur dioxide when equilibrium is reached. The final pressure is 1.4 atmospheric. You are asked to calculate the partial pressure of sulfur dioxide, oxygen, and sulfur trioxide at equilibrium. You are also asked to calculate the Kp for this reaction. Once again, we will construct the ICE table. This looks exactly very familiar to what you have seen in the Kc expression, so it's not entirely different. At the initial, you have 3 moles of sulfur dioxide, 3.6 moles of oxygen, and 4.8 moles of sulfur trioxide. You have found at equilibrium that you can have 2.6 moles of sulfur dioxide. Therefore, the change in amount of sulfur dioxide will be 0.4 moles. Because sulfur dioxide and sulfur trioxide are in a 1:1 mole ratio, you would have gained 0.4 moles of sulfur trioxide. Since the mole ratio of sulfur dioxide and oxygen is in the ratio of 2:1, you would have lost 0.2 moles of oxygen through the reaction. Hence, at equilibrium, you would have 3.40 moles of oxygen, and at equilibrium, you would have 5.20 moles of sulfur trioxide. Now, using the partial pressure calculation through the Dalton's law of partial pressures, the partial pressure of sulfur dioxide would simply be the number of moles of sulfur dioxide at equilibrium divided by total number of moles of gas. That will give us the mole fraction of sulfur dioxide multiplied by 1.4. That will give me the partial pressure of sulfur dioxide. The partial pressure of oxygen can be also calculated in a similar fashion. When you find out what's the number of moles of oxygen divided by total number of moles of gases multiplied by total pressure, that will give us the partial pressure of oxygen. The partial pressure of sulfur trioxide can also be done in a similar manner, where you get the number of moles of sulfur trioxide divided by the total number of moles of gases multiplied by 1.4, which is the total pressure. That will give us the partial pressure of sulfur trioxide. Using this partial pressure that we have calculated in the box on your left, you will be able to calculate the Kp. So the calculation of Kp will be 9.41 atmospheric minus 1. Now, in the next example, example 6, we are once again still calculating Kp, but this time round we are making use of percentage dissociation. You have SO2Cl2 gas decomposing to give you SO2 gas and chlorine gas. At a temperature of 375 degrees Celsius and at overall pressure of 1.01 times 10 power 5 Newton per meter square, a sample of SO2Cl2 gas was found to be 84% dissociated. You are asked to do 2 calculations. One, to find out the initial pressure of SO2Cl2, and the second calculation to find out the Kp for the above reaction under these conditions. Something to take note, that the underlying phrases refer to equilibrium conditions. And the PT, or the total pressure at equilibrium, is 1.01 times 10 power 5 Newton per meter squared. So once again, you see this ICE table. This ICE table looks exactly as the earlier ICE table you have seen in the earlier example. Now we have made use of Newton per meter squared because we have assumed that the volume of the vessel is kept constant. This is quite important because pressure will be affected by volume. So once again, you want to ensure that when you use the ICE table, you are actually talking about the amount of substances that's being changed. But because the Kp expression requires you to use partial pressure, therefore it's sometimes convenient to leave the ICE table in terms of pressure. But once you cannot ascertain that the volume of the vessel is kept constant, you should use moles as your units for your ICE table. But in this case, we have assumed that the volume of the vessel is kept constant, so we have assumed and let X to be the initial pressure of SO2Cl2, which is found below, and we have assumed that sulfur dioxide and chlorine has not been dissociated, so their initial partial pressures are 0. The question told us that 84% of SO2Cl2 has been dissociated, so it will be minus 0.84x. Since SO2Cl2 and sulfur dioxide is in the 1:1 mole ratio, sulfur dioxide would have gained 0.84x. And chlorine, also similarly having a 1:1 ratio, would also have gained 0.84x. At equilibrium, you would expect that SO2Cl2's pressure will be 0.16x. For sulfur dioxide, it will be 0.84x. And for chlorine, will be also 0.84x. The sum of all the equilibrium pressures, 0.16x plus 0.84x plus 0.84x, will be equals to 1.01 times 10 power 5. You can solve for x. And once you can solve for x, you can find out the second answer, which is to ask you to determine what is the equilibrium constant, Kp. Once you get the Kp expression, you substitute all the numbers into it, you will eventually get 2.42 times 10 power 5 Newton per meter squared. This is the end of the video that talks about how we can apply the ICE table in chemical equilibrium calculations.